It looks like it's official. We can start. Welcome back, everyone. So today's class is pivotal in a certain sense. When we come back next Monday, February 5th, that's when we'll be doing our first exam. I did send out an email to everyone who is coming in through, say, the Pocatello campus, and I think I got that date wrong. Thanks to that student who corrected me there. It is scheduled for Monday, but for the folks in this section of the class, section 11, we have to work within the realities of the Pocatello Testing Center and their ability to schedule the people in the class. So if they can't fit you in specifically on Monday, then you'll just have to work within their schedule. Also, you don't have to take the exam during the actual exam time. So it'll be all up to how it all fits in. I sent out emails and such to call out the testing center and they'll work with you to find a common time. Aside from that, for folks who are on this section, that's assuming you're on the Idaho Falls campus, our exam is just going to be in this classroom as if it was a normal class day. I'm writing our exam as a 75-minute exam, but that includes extra time baked into the exam to check your work. So not everyone will take the full time, but I encourage you to take as much time as you need. Definitely double check your answers, that kind of stuff. And if you're ever foggy on an answer, oftentimes your first intuition was the correct one. Let me get back down to where we're at. Let's see here. Other things to mention in the announcements are, let's see, it's definitely on Monday. And with our upcoming quiz, this one right here I indicated is going to be a really good exam one question. I'm going to ask a question that's very similar to that, just changing some things around. In fact, really all of your quizzes were designed in the sense of they came from actual exam problems, or they're written with the intent of this would be a good exam problem that I might ask. So if I was in this class, I'd always collect all my quizzes, look over them again, and at the end of the semester, you could just put them together. That's a sample final exam set in a certain sense. If we look at quiz 3, then it's one of these kind of questions. And that's one of the reasons why I want to give a hint. This one will be on exam 1, because this is one that it's not terrible, but it's tricky to get fluent with. It takes a little bit of practice to get a handle on these kinds of problems. If you need some practice, you can take a look at the ones that we did in the prior sections in 2.5, I believe one in section 2.3 as well. Also, when you're doing these kind of problems, just a reminder to everyone in the class, if you have a question, you can always email me your question. You can take pictures of the work you did, whether it's digital or on paper, and I can work with you on that question. Even on this one, if something on here just doesn't seem right, don't hesitate to reach out. I'll be very happy to help. Well, other questions, folks, about our upcoming exam or otherwise? Okay, well, the definite coverage is up to these sections right here. And our course is kind of strange. We don't have a lot of time for actual reviews to put in. So we have to go to section 3.1 just to not get too far behind on the schedule. But some of the stuff we're doing in 3.1 is this kind of content. Here, this is all about limits. Here we're defining a derivative, but that's just a fancy new limit. We'll practice taking limits in section 3.1. And let's see, only other announcement I have is quiz 2 is due today. I also want to mention, as far as quizzes go, think of the due dates as really kind of pacing. If you're getting all your WebAssign homeworks done and all of your quizzes done on those due dates, that's the benchmark for being fully caught up for this course. But I'm going to be forgiving with quizzes as well. I can accept them late. So if something happened in your life, maybe you just got thrown into an extra shift at work or car broke down, stuff like that, illness, reach out to me. You can send in your quizzes late and that will always be okay. I think I'm running out of announcements at the moment. Any other questions or comments, folks, before we jump into 3.1? Okay, oh, thanks. So now in section 3.1, we're doing our major objective of the course. There's no purpose to do all of these limits, is all we're doing is limits. Major reason behind this is it defines continuity. That's what we did in this section. And limits now define the derivative. Here's the refresher on that. There's a little graph that we drew out painstakingly. If we have, say, a curve, the one in black, y equals f of x, the major question we'd like to ask is, what is the slope at any single point on that curve? We want to know the instantaneous rate of change, in other words. And this could have a lot of physical meaning. For example, I'll take off these axes for the moment, but this could be time. and this could be distance. If that's the case, then that purple right here is the instantaneous rate of change at the moment of time A being passed. In other words, suppose time A is the moment you looked at your speedometer while driving. Slope of this line is giving you your instantaneous velocity at that moment. So well, that's just one example of physical intuition behind these, but there's many other things along those lines. Essentially anything that you could write as a rate, distance versus time, or maybe it's something along the lines of money versus volume or something along those lines, you're dealing with the derivative in some way, somehow. So the derivative is found by calculating this first. That would just be the slope of the secant line. But to get the actual slope of the tangent line in blue, you have to allow this point in green to get closer to the point in black, meaning A plus H has to get closer to A, meaning even further, H has to go towards 0 and the limit. So that's why the limit is defined in that way. It gives us the actual slope. Well, any questions, folks, with the run through or the warm up on that diagram? Okay, well, this gets us primed for what we're about to do. We're about to do exactly this. We are going to calculate this tangent line on this function right here. I did make a change on these notes. Let me remind myself, this was revised today. I like to look at my work and actually see how the notes look by previewing what I did there and proofreading it. And I felt a power 3 kind of inappropriate. I'm not going to ask higher power problems like those. Not that it's bad, it's just more algebra, less focusing on the actual calculus. And I don't think I assigned anything along those lines in WebAssign. So if you printed out the notes already, please change the power of 3 there to a power of 2, and you'll be all set. That's the only revision. It says, find an equation of the tangent line to this curve at the point 1, 2. First thing I would do is definitely take a look at the definition. Here it is, reduplicated. And in the definition, the immediate thing that they do is they define function notation, y equals f of x. So however you have your information stated, visualize this as an f of x, because function notation is how we typically define formulas when we're using functions. So first thing I would probably do here is write f of x equals x squared minus 5x plus 6. That gets us started. We didn't do anything major, but if we're going to use that formula, we need to take that notation of the problem and put it into a compatible notation that we're expecting to see. So it now says the tangent line to the curve y equals f of x at the point a f of a is the line through P with this slope. But now we need to focus on a f of a. We need to say what it is in our problem. And here it is. The moment they give you a point, you can say a equals 1. F of a, that's going to be the second coordinate. So in other words, it's f of 1, which is 2. So we now have that part of the notation, and that helps us out because we need to know exactly what a is and what f of a is. They've in fact provided it right here. We just needed to know that by walking through the notation. Next thing we're going to do is take that limit. But if you're a fan of divide and conquer, you might not tackle the whole thing. I think it's kind of fun to just go for the whole thing sometimes. So we'll do that sometimes just to show that style. But for the divide and conquer method, it's not a bad idea to do an element of the problem first. Notice we already did f of a, it's 2. That was just observing the point. Let's do f of a plus h. That sometimes is the algebraic-y, nasty part of the problem. Any questions first, folks, before we calculate that portion?
How did we get A? Did we just assign that, or did we take the first point in the parentheses?
Exactly as you said, absolutely. So whatever the first point is, that's going to give you your A directly. And the second point will always be your f of a right there. Absolutely.
Oh, okay, thank you.
You bet. Thanks for asking about that. Other questions so far? Okay, well, let's maybe color code this thing because we're going to make a substitution with it. Let's calculate to that portion. I'll do it on the far right side, f of a plus h. First thing you want to do once again is input what a is. We go back to that first point and have a is 1. So this is f of 1 plus h. Now at this stage, we're using function notation in earnest. That 1 plus h is in whole function going inside this function. So it replaces x in that location and that location. But before doing those, here's the strategy. It's a little bit of a review at the moment. Where you see x squared, write out this way, just a placeholder to power 2. There'll be -5 times x, but put in a placeholder for x, and then a plus 6. Usually this is the easier way to write out the next step right here in function notation. The 1 plus h just plugs in into both of those empty slots. So here's 1 plus h, 1 plus h. Again, in summary, if you calculate f at 1 plus h, you're just putting it here, still squaring it, and here, still multiplying it by -5. Does that look all right to folks so far? Okay, let's work through now expanding this thing. So I'll take the extra step to write this as 1 plus h times 1 plus h. We'll FOIL that out in the next step. You can do it right now if you like. Here, distribute -5. So -5 minus 5h, and then copy plus 6. You can see why sometimes breaking up the problem is not a bad idea. This is kind of a problem unto itself that we're going to plug back into this formula. So next step, we'll FOIL this out. We'll get 1 plus h. That's distributing 1 into the group. Distribute h into the next group, and you get plus h squared. We already have some like terms. We can combine the -5 with the positive 6 to get plus 1 minus 5h. Now at this stage, we still have more like terms. Let's combine those as well. We have the 1 from here to here, so 2, plus to power 1, here's 2h, minus 5h, so -3h to the power of 1. Oh darn, I never seem to plan ahead on those. Let me change that plus to a -3h. And there's only one power 2 on h, so the h squared copies it, plus h squared. This is a good step to look and be really careful we didn't drop one little term, because the limiting process here is extremely sensitive. Notice you cannot use direct substitution at all in this thing. Continuity is off the table immediately. You can't plug a 0 in there for h. But the limit does exist, and the only way we're going to actually calculate this limit is by canceling that h right there. We made even one mistake, all bets are off. We're probably not going to cancel h. We're just going to get stuck on the limit. So if you get stuck, it might be something really small. Let's double check we've got everything. 1h squared minus 5 minus 5h. I think we're okay. That plus 1 looks fishy, but that's the -5 plus 6. So let's now go back to here. We're ready to calculate the slope. It's now equal to the limit as h goes to 0. When you write out all of this, the picture you want to have in your mind is you're now doing this. You're taking the green curve, moving the dot until it turns into the blue curve. That's what's happening in the background now. So limit as h goes to 0 of, let me kind of make that go more horizontal. First thing we'll plug in is f at a plus h. And here it is, 2 minus 3h plus h squared. Next portion is minus f of a. So minus, coming back down, f of a was f of 1, which was 2. But at the end of the day, whatever that f of a comes out as, it's always the second point right here of the given point. It's always going to just be that 2. So minus 2 goes in. And then we divide the whole thing by h. So there it is, folks. That's our derivative. We just now need to simplify it, use continuity after we cancel h, and we'll be on our way in this problem. There's already a direct simplification. These 2's will cancel, and that's by design. If I couldn't find a way to cancel that 2, you also wouldn't have been able to get rid of this h down below. Everything that doesn't involve h has to eliminate some way, and so you're only left with terms involving a factor of h. That's what allows this h to divide through, and that means we're on the right track still. So on the next step, it's limit. H goes to 0. You can cancel your h here if you're not too worried about it, but make sure you cancel it on both terms in the numerator. Sometimes the author goes this way just for safety, factors out the h. He's a -3 plus h. Whole thing is still divided by h. And now here's the consolation that we required. We're stuck on this limit. Every time you write down the formula, you're stuck. You cannot even evaluate the formula. But if the derivative does exist, if you can calculate the slope, you're going to come into this situation every single time. H will eliminate. That's good numerical evidence. You didn't make a single mistake. Now direct substitution is going to work for us. Let me write this step one more time just to make it clear and readable in the notes, although you can do it right at this step if you like. The prior step, I mean. Now this function is continuous with respect to the variable h. You can just plug in your 0, and when you do that, the h converges to 0 through the limit. I mean, it makes sense, right? If h goes to 0, that h is going to 0. It's just gone. If it was 5 times h here, it's 5 times 0, and it's still gone. Tells us the slope is now -3 exactly. So this curve doesn't have any physical intuition behind it. It's just a mathematical object. But if it represented something like a rate of change, a speed, or something like that, that would be the instantaneous rate of change that we just found. But what we're going for is this. You have to be careful with the instructions. Sometimes the problems just want that value. We'll see that in the notes. Other times the problems want the full tangent line. And so there's a little bit of a few extra steps before we get too far. However, if this was an exam question, I would think of this as like 8 out of the 10 points. This is the major calculus so far. Well, let's go and get that tangent line. To get the tangent line, really, whichever way you'd like to write down the equation of the line, completely up to you. I typically go with this method. I take the point, call it x1, y1, and it's 1, 2. Next thing I do is I write down the slope, just so it's available right where we're working. M is -3. And the equation that I typically use to build out a line goes y minus y1 equals the slope m times x minus x1. So this is our point slope method. All we're going to do is plug in the information, solve for y. Any questions at all, folks, to this stage? Okay, let's throw this stuff in. So there are 1, 2, 3 substitutions we're going to make all in order. Y stays as y as a variable, and let me grab an actual pen just a moment. So we'll get y minus, when it refers to y1, it's the second coordinate of 2 right here. Equals, this is the major thing. We're going to soon be calling this the derivative. You know what? It deserves a good color. Let's give it this color. So here's our slope plugged in. Then it'll be x, that stays as a variable, minus x1, first coordinate right here, so x minus 1. At this stage, what we ought to do is solve for the variable y. So let's distribute the -3 through and add 2 to both sides. Let me scroll just a touch. So we'll have y, let me actually do that in stages, y minus 2 equals -3 plus 3. Oh, hang on, let me put in -3x, don't want to forget that, plus 3. Finally, we can add 2 to both sides, and we have y equals -3x plus 5. And my claim is, that thing there is the tangent line equation. So that means we did it, folks. We calculated 2 things, our very first derivative and our very first tangent line, all in the same spot. Any questions at all, folks, with that full process there? Okay, after doing this much work, the good news is that there is an extremely strong check with this. The check is going to give us fantastically high amount of numerical evidence. You did everything right. It's not perfect. It's not a proof. You could have made several mistakes in the work here that just worked out right, but that would be absolutely rare. Our check is really this diagram. The blue line right here is the best local linear approximation to the function y equals f of x. That means if we plot both functions, the original function f of x and the tangent line equation, we should be able to zoom into that spot and show that the functions become more and more the same the closer we zoom in. So let's show that next for what we did here. And if we made a mistake, we will find that out immediately and we'll definitely correct it as well. So let's go to Desmos to start. First thing to input is the original function right here, or you could be using that function as well. I like the function notation, so I'll go f of x is x squared minus 5x plus 6. So there's our quadratic. This is happening at the point 1, 2. Oh, sorry. Yes. Thanks for spotting that. There we go. X squared minus 5x plus 6. So there's our correct quadratic. Thanks for spotting that. And we're interested right at 1, 2. So we're looking at a point right around here. If 1, 2 wasn't actually on this graph, then the whole problem would have been a lie. That has to be an actual point on the graph. I'm having a hard time landing on it, but we did have 1, 2 on there. So now the next thing to put in is the tangent line equation. So negative 3x plus 5. Let's give it a y equals. And here's what it looks like for us. Already, that looks like we did everything correct. That blue line is the tangent line equation. But let's be real sure. Let's go back to 1, 2. Here's our common point of intersection. And let's say this one more time. The tangent line is the best local. You have to be around here. Linear, it is linear. It's an approximation to the original function when x is 1. So let's see that in action. Zoom in on this thing. And before very long, the point and the curve become indistinguishable in this region. So if you're estimating, you'd have to get the values here on the horizontal axis. But if you're in this range and you're just solving an equation, you know what? The linear equation is going to work just fine. You don't have to do equation solving with the quadratic. All you care about is right around here, a value at 1. The linear equation works just fine. Let's zoom back out on that to show kind of the bigger picture. And visually, this is what tangent lines should look like. Hitting the curve tangentially looks like this. It intersected in this one location and they just went off in that direction and that direction. Let's take here just a really quick screenshot. And add it to the notes. Well, we've got our tangent line equation. And the reason I want to add that to the notes is once you have a tangent line equation, there are certain questions that become more confusing than are necessary as a concept question like this one. But it is an important concept question. There's going to be one like in WebAssign. So let's try working through this example too, with this up above as our intuition on why things are going to work the way they should. It says here on example 2, if an equation of the tangent line to the curve y equals f of x at the point where a is 2 is that equation, find f of 2 and find f prime at 2. In my view, that is the massively important concept, but this is still important right here, finding f of 2. Now let's work on this by analogy of what we see above in the graph that we calculated. The point wasn't a equals 2, it was a equals 1. And the problem is not giving us the function f of x. So let's kind of imagine that's our scenario. We have no f of x, just like in this problem, yet we want to calculate f of 2. Well, on this diagram, the good news is you put in 1, here it is. Oh, that's not going to work. I always forget I have a marker loaded. When you put in 1, you intersect right exactly here, and this is a point in common with the now unknown function. The tangent line matches up right there, and so you could say f of 1 equals the output value of 2. In other words, just use the tangent line. They told us that this one was the tangent line. So it means if we want to calculate f of 2 in our current situation, all we need to do is go f of 2 equals, we don't have the function, but we know the function matches on that tangent line equation. So just plug a 2 inside there. It'll be 4 by 2 minus 5. And so we get a value of 3 altogether. So kind of weird, but that's just the nature of the tangent line. You can recover a function value without knowledge of the original function. Who knows what f of x is in example 2? Any questions, folks, with calculating the f of 2 here? Okay. I mentioned f prime of 2 is probably the bigger thing. I mean, it looks weird. What is f prime? What we think of when we say f prime is this. F prime at 2 is going to be equal to, and we'll say this a lot because this is the geometric interpretation of the derivative, and it has a sneaky way of always coming back in these kind of courses. So f prime of 2 is the slope of the tangent line to y equals f of x at a f of a. It's quite a readout, but that's what we mean by derivative. Putting a prime here is just telling us we're dealing with a derivative in that case. And the bigger takeaway is, once again, that one right there. The whole purpose of example 2 is it's a reminder that every time you calculate a derivative, it is literally each and every time that slope right here of the tangent line. So now, with that knowledge in mind, let's calculate f prime at 2. Anyone see what that value should evaluate to? Anyone in Zoom say spot what that ought to be? It's kind of like following arrows in a certain sense. Let me show you how I would probably think of this. It says in this, which is kind of a formula in a sense, the geometric definition is the slope of the tangent line. So first thing you want to go is find your tangent line. This one was stated as being our tangent line in this problem. So that means now we have to grab the slope of that tangent line. But the good news is that thing is in slope-intercept form. The slope is right here. So the derivative then is exactly 4. So again, whatever the slope is right here refers to the instantaneous rate of change of the original function. And so if a tangent line is stated, they gave us the derivative. But it's a hard concept to tie together. Again, that's the purpose of example 2. It's more of a reminder of what's right here more than anything else. Well, we'll have lots of reminders of the geometric interpretation of the derivative. It just keeps on coming back. But any questions at all, folks, with what we did here on example 2?
I just have a question as to how f2 and f prime 2 are different.
Sure, absolutely. So this f of 2 is like referring to the original function right up here.
Mhm.
And so the original function matches on the tangent line. And so what we did was we plugged 2 right here for x, and then we just calculate all that out to get the 3. So that's what happened with this one right here, just the ordinary function value. But once we go down to this one, the moment you see that little symbol here, it's hard to read even. Let's zoom in on it. That one little symbol is the prime that we're referring to. Let's actually say it right here. This is read as f prime. But that f prime is now only referring to one part of the tangent line. It's always just the 4. Whereas f of 2 just means plug 2 here and take 4 by 2 minus 5. Does that make sense so far with your question about the difference between the two?
Yes, thank you.
You betcha. Thanks for asking about that. Other questions or comments at the moment? Okay, well, now that we have some work with these derivatives, some intuition of what they look like, how they're calculated, and what they're trying to say, they're trying to give us a slope. Let's start calculating a few of them. So here's a tricky derivative. Here we've restated a definition just to help us out. The derivative of function f at a number a is going to be denoted by f prime of a, and it's exactly this limit. Now, if you look at that, that should feel like deja vu, right? If you take this right here, let's compare them side by side. Sorry for the sudden scrolling. There we go. So just to compare the two, here's that other definition. Definition 2 says the tangent line to the curve y equals f of x at a point is aligned with that slope right there. Looking at the limit, this limit right here is exactly the same as this limit, no difference. And so now they're saying the derivative of a function f at a number a will denote by the f prime at a that we just took a look at, but it is literally the slope of that tangent line each and every time we go to calculate it. This limit, however, is not guaranteed to exist. It can fail, and there's lots of ways it can fail. Maybe we don't have continuity where a is. We lose continuity. We've also lost differentiability. We'll find other ways differentiability can fail. It's kind of surprising. But for the moment in these notes, we're only going to calculate derivatives that we know the limit is going to exist. So let's calculate f prime of a on that function right there. We kind of did a preview of these sort of limits when we were in section 2.4, the algebraic method of limits of numbers at finite values. We had to take a limit of functions that were fractions like these, which meant the algebraic step is add up the fractions. It gets a little bit wild here, so let's take this and be really careful in our work through it with it. So that's the original function f of x. When it says calculate f prime of a, it means you're looking at the graph of that. This is the wrong graph, but just for a visual, you're looking at the graph and you're trying to find a function that's going to output the slope of the tangent line at any point a you give, not just a specific point anymore. So it's like we're trying to do an infinite amount of work, but what we're really doing is we're taking a function, we're defining a brand new function from the old one. Its derivative is just a function in its own right. So this could be called f prime of x, or f prime of a is not a bad way to start either, as the author usually does. First thing you would do is, not bad to start there, it reminds us what we're calculating, write down f prime of a. Next thing I would do is write down this step right here. Even if it's available on paper, sometimes it's good to just write it down because now, I mean, that's one of the more important limits in the course. And the more you write it, the more it's just going to seep into your mind. It's going to be second nature to write limit h goes to 0, f at a plus h, minus f of a, all over h. So there's our limit. Here's our function right here that we're going to work on. And the strategy on this one, when you see fractions are in the problem, is this h in the denominator, we can actually factor it out. Let's write limit as h goes to 0, dividing by h is just the same algebraic form as multiplying by 1 over h. The reason for doing that is the numerator is kind of ugly to look at. F at a plus h goes here and plugs a plus h and x in two locations, here and here. Here's how it would look. Forget I can't write while that's selected. 2a plus h, 2 times the group a plus h plus 1, divide by, down here, plug in a plus h, plus 3. Then it's going to be minus. This one is always the easy one. In some problems, it's just a number if they gave you a point. If it says calculate f prime of a, you're literally just going up here and interchanging x for a. So that's going to be 2a plus 1, divide by a plus 3. And if we knew the value of A, all of this would simplify, but we don't want to say a value for A. We want this to be as generic as possible. We want to find the derivative for every value A where the derivative would exist. So here's how the limit looks so far. And this is where it gets nasty. It's good practice, though. Sometimes mathematics is more about organization, being methodical, and extremely careful when things get messy. So this is one of the times where things get really messy. First thing I'm going to do is rewrite this, but let's make our fractions a little bit longer because we need the least common denominator now. There'll be lim for the limit. H goes to 0. 1 over h multiplying. And that's a little bit much. Let's go this way. I want a parenthesis, and that should do the job. Might be a bit overdone, but better to have extra space than not enough for organization's sake. In this numerator, it's good to expand it. It'll be 2a plus 2h plus 1. For this denominator, what I'm going to do is associate it. So just wrap it around with parentheses, a plus h plus 3. Then we have minus to minus, and nothing much happens here. Let's just put in 2a plus 1. A plus 3 with parentheses is a good idea in the denominator. And actually, we should probably associate every portion. Let's put a parenthesis around that numerator and around the opposite one as well. Okay, so we've got our fractions expanded. Now, the step that we used when we were faced with this situation in the prior notes was we just are trying to complete the denominators, make them identical. It's not identical, we're missing a plus 3, so we just throw it in right here. It must also go into the numerator to not damage equality. That still has to be maintained. We need an equivalent algebraic form. Over here, we just do the next thing. A plus 3, we have that over here, but we're missing a plus h plus 3, so we throw it in. A plus h plus 3 below and above. Here's where there's a really important reminder about limits. You almost always want to leave your denominators in a factored form. In fact, I can't even think of a certain time where I would want to expand out my denominators. I'd have to think about that and come back to you with that question. I would almost always leave my denominators factored. However, the numerators have to be expanded. They need to be expanded, like terms have to be combined. We'll distribute across a negative, and our hope of hopes is that somehow, some way, that h goes away. Because the moment it's gone, you're just going to use direct substitution. You could plug 0 in for everything else without a problem. It's that h right there that's stopping us, and it doesn't go away because it came from here. So this is the setup. Now the algebra really starts getting going. We're going to start expanding things. Any questions or comments to that stage so far? Okay, let me not scroll too much. It's good to see the original function, at least before we go too far down. And here's our next step. Take the limit as h goes to 0, 1 over h. We're going to combine these two fractions. So now I'm going to multiply by one really long fraction bar, minus in the middle, but I'm not sure where the middle is going to be until we expand, so I'll leave that off for the moment. And here's the stage where we want to go as methodical as possible. If you go slow at this step, you will get through these problems much faster, I guarantee it. I want to distribute from the blue group. That'll be a 2a squared, 2ah plus 2ah plus a. After that, let's distribute the positive 3 from the group in blue. This will be 6a plus 6a. This will be plus 6h. And here to here, it will be plus 3. Not so bad, but we have a lot of terms. Now, the reason we're being so methodical is it is so easy to make the tiniest mistake and then h won't cancel. We just get stuck on the limit. So now let's expand this one out carefully. That negative sign is a nuisance, and there's a couple strategies here. You could take this negative and distribute along with everything else, I think that's kind of shady. Me personally, if there was extra negatives, I'd probably make a sign error. If you want to be as careful as possible, leave it right there and distribute on the next step. So being careful means there's a lot of additional writing, unfortunately. If you don't like that, here's another strategy you could use. I won't use it on the notes because I've been alerted by people. It's pretty confusing when you do this. But if it's valuable to you, I'd say take this step. That negative sign can change. You can call it a positive sign, and that means the negative is distributed into a numerator. It would only distribute into one group, here and here. So you're distributing a negative 2a and a negative 1. You've essentially saved one big step by doing that. Does that make sense to folks seeing it that way? Awesome. So you can force distributions of a negative without worrying about too many sign flips. But for the notes, let's do it as careful as possible and just leave that negative right there. Now this time I'm going to distribute from the black group. I think it's a little bit easier distributing off the group with less terms. That's just a personal opinion. So I'll multiply here to here to get a 2a squared. Here to here gives us 2ah. And last, here to here is going to be plus a 6a. So that finishes off the 2a distribution. And this one's almost a freebie. Distributing 1 just gives you a plus h plus 3. So we'll just write that in. Plus a plus h plus 3. Finally, we need to write in our denominator. It's just going to be the common one between these two. Let's write in a plus h plus 3 times a plus 3. So it's gotten a lot uglier before it's improved and started simplifying. Next thing we're going to do is distribute the negative sign throughout, collect our like terms, hopefully cancel that h, and we'll be on our way in this problem. So here's our distribute the negative sign step at this moment. Starts with lots of copying. There'll be limit, h goes to 0. This time I'm going to combine these two fractions. So instead of two fraction bars, let's write one really large one. H here is just going to multiply right over here into this denominator. So it's h, a plus h plus 3, a plus 3. And I'm going to copy all the way to this step. 2a squared plus 2ah plus a plus 6a plus 6h plus 3. There we go. Finally, let's catch our breath. Distribute the negative into this group just implies we're flipping all the signs. Minus 2a squared minus 2ah minus 6a minus a minus h minus 3. Okay, let's pause and catch our breath here. Does that look right to everyone at the moment? Okay, here's where we're going to determine, are we on the right track? Recall, our goal is direct substitution of h goes to 0, means we have to eliminate that h. But if we have to eliminate that h, any term that doesn't involve h must go away. So 2a squared must have an opposite. There it is, negative 2a squared. This doesn't have to cancel, but it might. And in this problem, 2ah does cancel with its opposite, negative 2ah. We're more worried about the positive a here. That one must eliminate in order to complete the limit. And yeah, we have a positive 8 and a negative 8 clear over here. Down the line is positive 6a, and I see a negative 6a. It's getting a little bit easier now that things are getting eliminated. This is the satisfying step in some sense. At this stage, we have a positive 3, negative 3, and negative h, 6h. Those are the sole survivors, so just 5h is all that's left in the numerator. We're ready for the next step. Let's scroll just a touch. We now have the limit as h goes to 0 of, let me double check, 6h minus h, so 5h, all of which is being divided by that full-on denominator, h, a plus h plus 3, a plus 3. This implies we have the cancellation that we need. That h is now eliminated. because it cancels with that h in the numerator. So now direct substitution is finally on the table for us. The remaining function is continuous in the variable h, even when h goes to 0. That's in the domain now that we eliminated that h. So this h goes to 0 in the limit. And that means our work is pretty much complete now. We just need to write down our results. There's a survivor of 5 in the numerator. The denominator is a plus 3 times a plus 3. But those combined, we can simplify this to 5 divided by a plus 3 squared. And finally, that's it, folks. That's the derivative of that function right there. What it does is, if you plot this function, go to any point in the domain of that function, as long as you're not at -3, plug in the x-coordinate, and this will tell you the exact slope of the tangent line equation. If this had some physical intuition, it would also tell you the instantaneous rate of change at that time. So it's quite a process. This one was meant to be kind of a worst case scenario. There is a fraction type problem in the WebAssign homework, but I don't think it's going to be that bad. So this is as bad as it could get for our course. Any questions at all, folks, on the conclusions?
Yeah, really quick going back, sorry. On the second step, on the denominator, a plus h plus 3, where did we get that? Sorry, one above that.
The one up here?
One step above, sorry.
Oh,
So,
over here,
yep.
Gotcha.
Yeah, where did that a plus h plus 3 in the denominator come from again?
It should have came from, but let's double check this, see if we can track this through. Sometimes that's a pretty good skill to practice as well, trying to reverse engineer where did something come from. So this part right here is conflated with the negative signs, so it should have came from that location. But let's double check it and show it as well. F at a plus h. If we were to evaluate that, we're going to plug it into this function, but here's a strategy for doing that kind of evaluation. It would be, for this function, write in a 2, where you see an x, put in a parenthesis, and a plus 1. So that's the numerator. The denominator, I'll put in another placeholder for x, plus 3. And then for this a plus h, it goes into those two locations, but we've already blown up a placeholder here and here. So a plus h, a plus h. So finally, that's what connects with, let me double check though that, yeah, that's what goes from here to here. We drop the parentheses around that denominator and distributed 2 through this denominator into that next step. But does
Okay,
that make
yeah,
sense?
that helps. Yeah, that makes perfect sense. I just gotta remember that placeholder part, and that makes it completely click.
Awesome, glad to hear that. Yeah, and I agree with you. Function notation, when I was learning this stuff as a college algebra student, it did not make sense until the instructor started writing it out like this for me in office hours. And finally, it all fell into place. It's kind of weird. A change of view kind of makes things more sensible. Other questions or comments so far, folks, with this one?
Yeah, maybe I missed it, but where does the 1 over h come from at like the very beginning?
Oh, this one right here?
Mhm.
What I was out with that 1 over h was, I was trying to avoid this kind of scenario. Let me see if I can copy this. Oh. Maybe not, but I think I could get a different way to view this. Okay, here we go. I think this will work out. So the reason I did this 1 over h was, it was more of a stylistic choice, not something completely required. If we wrote out this limit without that change, it would have came in this format. It would have been f prime of a is the limit as h goes to 0. This f of a plus h would turn into that stuff right here. So it'd be a 2 a plus h plus 1, a plus h plus 3 minus 2, a plus 1, a plus 3. And then we would have divided by h in this kind of way, like that. So that's how the limit would originally work. And there's no reason why you wouldn't want to copy this down. This is completely correct. It's completely fine. The only downside is it takes a lot of vertical space on your notebook when you write it out this way. And so the step I took to get to here, the 1 over h, you can think of it in two ways. That h can factor out and become a 1 over h, or what did I just do? Oh, clicked on something. Or we could go like this, multiply by the reciprocal of 1 over h, you would get, I said that weird. Let me try again. Multiply by the reciprocal of h over 1, and the 1 over h would emerge right here. So that's essentially all we were doing with that 1 over h, trying to get it out of this kind of arrangement, just to have more vertical space to work with. But does that make sense on how that h emerged right there?
Yeah, for sure. Thank you so much.
You bet, absolutely. Other questions so far? Okay, so that's calculating derivatives. One thing I did want to actually add to this is, with our work, whether it's a quiz problem or exam problem, there's always an expectation of correct limit notation. It can be a bothersome sometimes, but correct limit notation meant we had to track this, it's tedious, I know, this, as limit as h goes to 0. Then, once we evaluate the limit through direct substitution, when h actually did go to 0, we have to drop the limit statement. So no limit statements when we get to our very end answer. And as far as losing points, if you forgot a limit statement, let's say on exam 1, maybe you didn't write limit as h goes to 0 on your entire exam. You're not going to fail the exam. I'm only going to dock you points once, and I'll circle it and say, be sure to use correct limit notation. It's more of just a reminder, and losing a point, it's just a small reminder as well. Well, that's calculating derivatives so far. And let's see what we've got going on for our next one. This one's going to be the application problem for the day, and I think we just have enough time to take a look at it. What we're going to start with is, well, some of collected results from before. The tangent line to y equals f of x at a point A of f of a is a line through a f of a whose slope is equal to that thing, the derivative of f of a. And we can also think, if we're talking about physical problem, f prime of a is the instantaneous rate of change at time a, or when x is a. Oftentimes when these applied problems, we might think of x as being time. And so you'll see t's emerge, like in this problem down right here. T might not be the world's most favorite variable, but you can make a variable make sense with what's going on in the problem. It's always worth it to write in a t. So here's what's going on in example 4. A rock is thrown upwards on the planet Mars with an initial velocity, so the moment it leaves your hands, it has 10 meters per second of velocity in meters after 10 seconds, is given by so-called position function. Position function is indicated as s, and this must be something from physics. That's a weird choice of a variable. Looks like the number 5. But just like we did in some of the prior problems, even if a position function is given as s, we often work with the function notation, because function notation is how our interesting objects are often defined in calculus. So we'll work with this as our position function. It says, find the velocity of the rock after 1 second. Here's what we can say just for some background information. If you start with the position function, say you call it s. If you do this, you're talking about the derivative of the position function. If you give it of a, they're saying at a specific point, but if you leave it just like this, you're just referring to the whole function. S prime turns into v, where that's the velocity function. And one thing that's kind of interesting about these is you start with the function, either call it s or f of t. If you differentiate it, you're going to get a new function. V is going to specify the velocity at any time if we calculate v prime at a. But they're asking us to calculate the velocity of the rock after 1 second, which means in this problem, we're setting time equal to 1 second. And we want to calculate v at 1. Recall, this is saying velocity of 1, which means it's the derivative of that function right there. Any questions so far, folks, with the different notations we're seeing on this problem? Okay, I want to add just a little bit over here. This part's the preview. This is stuff we're going to see later on. Might as well talk about it now that we're discussing derivatives. Suppose you differentiated S again. You really are allowed to do that. And if you want to indicate something's been differentiated twice now, well, you have to run it through that limit twice. That's pretty rough. We won't ever do it that way. We're going to use formulas for higher order derivatives. Let's imagine you did differentiate it twice. The second order derivative, or just simply second derivative, has 2 prime symbols now. But that means you're differentiating velocity. So that'd be a single prime on the velocity function. Going on this first line, velocity was the rate of change of position. The rate of change of velocity, that is what we mean by acceleration. And we can go even higher and higher, but we start to lose meaning of what are the new functions and what are they telling us. But a second order derivative is giving us the acceleration of the rock that's being thrown upwards. For us, however, we're going to calculate velocity at time exactly 1 second. That means we get to use this formula here. We specify time as 1 second, and that's going to be the value of A. I'm not sure where I want to put that. Yeah, let's just leave it like this and plug it in. So velocity at time 1 is going to be equal to the limit as h goes to 0. Up here, we're going to write in f of the 1. That comes from the 1 second right here. The time is 1 goes right there and right there. So 1 plus h minus f at 1 would plug in right here. Then the whole thing is divided by h. So that's the limit we have to take. Based on what we did above, this one is not going to be that bad, I promise. We'll get through this one in time. Sometimes, though, with starting these problems is half the battle. We had to stitch together a lot of information. We had to know we're talking about a velocity function, which is now the derivative of the position function f of t, and it's at 1 second, so one plugs in those locations. But it's really just redoing that formula for a third time now. Well, let's now work this through. Maybe let's break this one up like we've done in the past. Let's calculate f at 1 plus h first, calculate f at 1, and then we'll bring the results back together, completing the limit. So f at 1 plus h. Here's the reminder that calculators are allowed on the upcoming exam. For our exam on Monday, it could be either the TI-30XA or its slightly more beefy counterpart, the TI-32X2, TI-30X2S. The purpose of the calculator is more for problems like these. We'll use this as our official calculator in class, only because it's really easy to demonstrate. So first thing we want to do is plug in 1 plus h inside here. If this was a real exam question, and you're using a calculator to move through the question, you definitely want to put this on paper. This is how it would award partial credit. 1 plus h is going to go into this function, so it's 10. A group for t minus 1.86. A grouping symbol for t squared. So we've blown out to where t was, just left an open blank. And then 1 plus h will go in both of those locations. So if you show me this, just a few of the steps on paper before you start putting things into the calculator, that's how we can award partial credit on these kinds of problems. But I guess we don't really have a cost to use the calculator just yet. Let's keep on expanding this thing. On the first group, 10 distributes through, so it's 10 plus 10h. Here we can't distribute negative 1.86 because we need to deal with exponentiation first. So negative 1.86. You can go 1 plus h times 1 plus h to start. If you're comfortable foiling it there, I'd say just go for it. So second line, we've got 10, or I guess is the third line, 10 plus 10h minus 1.86. And now we're foiling this out. Distribute the 1 through, and we'll get 1 plus h Distribute that h through and you get h plus h squared. Kind of feels like deja vu. These kind of things show up a lot for these problems. I'm taking quite a lot of steps through this just to show the process. If you put 2h right here, instead of 1 plus h plus h squared, those are good kinds of shortcuts to take in this process. But for the notes, just to make them readable, sometimes I take those additional steps. So it's 10. On our next line, 10 plus 10h minus 1.86. Now, here's the step I must take, 1 plus 2h plus h squared. Almost there, folks. It just keeps on going. And sometimes, again, this is the value of separating out that portion of the problem, if you know it's boiled down to this. Next step is 10 plus 10h. And now we're finally distributing that quantity into the group. We'll multiply the 1, so negative 1.86. We have to double it as well. Let's get the calculator to work for us. 1.86 times 2. Good to have a calculator. I'm terrible at mental arithmetic, especially when it's a night class and we're all just a little bit tired. So that turns into a 3.72, and it'll also be negative. So negative 3.72h. And then negative 1.86 times this, nothing special, negative 1.86 h squared. Nearly ran out of space on that one. Well, that's one part. That's this right here. Well, let's move down and calculate f at 1. First, any questions, folks, on this expansion here? Okay, now for f of 1, here's where my comment was a little bit better targeted. I was saying, this is just a calculator portion. You're going to get a number here. But even though you're just plugging stuff into the calculator, on this step, it's wise to just write in 10 by 1 minus 1.86 times 1 squared. That way, if you miskey something in the calculator and your number is totally off from what it should be, I'll still give you most of the credit, essentially all of it, if that's there on paper. I'll just say, oh, that was a calculator issue. You didn't have any struggles with the calculus. You know that material. I try on exams to award credit for the actual concepts that we're driving for. So let's now put that in the calculator. We've got a 10 minus 1.86 is all it boils down to, so 8.14. So this one equals 8.14. Now finally, with all that work on the right-hand side, we come back here and start to complete the limit. It's now equal to the limit. As h goes to 0, I'm going to use yellow temporary highlight to show where we're grabbing stuff. I should probably try to keep these things separated. They're kind of glomming together. So temporary highlighting for here, we're grabbing this portion, which settled down to that statement. So let's plug that in as 10 plus 10h minus 1.86 minus 3.72h minus 1.86h squared. Phew, nearly ran out of space, but that's okay. Last portion we're taking is this right here. I should include that negative sign. I haven't put it in yet. Here's f of 1 at 8.14. But with a negative, we get in negative 8.14. Then finally, the whole thing is divided by h. And this limit won't be too bad at this stage. Really, this was the worst part about it, doing all that expansion work there. Any questions at all, folks, to that stage of the process? Okay, well, let's see what we can cancel off on this. Recall your ultimate objective. If you're calculating a derivative, whether it's v at 1, f at 1, or f prime at 1, or f prime at a, your goal is to eliminate that h. So let's take a look. We have 10 minus 1.86 minus 8.14. These two combine to negative 10, combines to the positive 10. So that is a cancellation right here. No harm double checking the calculator, but yeah, that looks about right. Next, we have 10h minus 3.72h. I don't feel very mentally spry. My coffee has worn off, so let's do it this way. Treat yourself to a calculator. It's allowed on exams. So 10h, or 10 minus 3.72, will give us 6.28 h's. So let's write in, I kind of did that a little bit early. Limit h goes to 0, the 10h here and the negative 3.72h from here combined to the 6.28 h's. So 6.28 h takes care of these two here and here. Then this one just copies in, so minus 1.86 h squared. We're just about there. Last thing to do is to cancel this h. We typically factor out the h in class, but we've done that a lot. If you want to see a different method, here's how it would look. You can cancel h right here and now. The caveat is you need to be particular how you cancel it. If you cancel it in just one spot, it must now cancel in every single term in the denominator and in every single term in the numerator, every one. Here, however, it's a power 2, so when it cancels, you just leave that h right there. That becomes an h power 1. So that's a way to do it if you like. If you went that route, your next step would be limit h goes to 0 of 6.28 minus 1.86 h. But how do folks feel about that? Is that an okay shorthand going from here to here? Awesome, I'm glad to hear that. Just keep in mind, it is a dangerous step. There's a reason the author doesn't do this very often. It's easy to miss that you have to cancel here too. Everything is getting canceled by one factor of h. But that means we did it, folks. H is eliminated from the denominator. Over here, h goes to 0 in the limit, which means the entire term goes to 0. And we're done. We'll drop the limit statement and just say 6.28. But we also want to give this thing some units. Recall the derivative is an instantaneous rate of change. That word right there is important. If your position function was given in terms of, let's see, position function s is in meters, your derivative is a rate of change of meters per second, which makes sense. That's what velocity should be, meters with time. So this 6.28 right here is meters. The meters came from the position function. It said, how many meters were you after throwing the rock per second? And the second came from, that's the independent variable right here, measured in time. So we did it, folks. That's our end result on this thing. Notice your derivative is positive, and so it means that rock, which was thrown upwards, 1 second later, the speedometer on it, if there was one, its instantaneous rate of change is moving upwards because positive 6.28 meters per second. At time 2, this is going to change. It's probably going to drop down because gravity is now acting on it, negating the initial velocity. And this thing will eventually turn negative. If you've got a negative sign here, it means your rock is now moving in the downward direction by whatever amount meters per second. Phew, well, we did it, folks. That's kind of a tricky derivative here because of its applied nature and that stuff. But any questions at all, folks, while getting through this material? Okay, I want to leave everyone in class with one additional idea. These derivatives are pretty hard. That's pretty admittable. We're doing this through a definition like this, the limit definition. And that's a good idea since we need to know where do all the derivative formulas actually come from. But there are formulas, and when we move to section 3.2, I want to leave you with a preview of what we're going to do. If you were to differentiate this function and throw in a value of 1, we're expecting a slope of -3. There is, in fact, a really fast derivative formula for this. The derivative of this function would be indicated as a y prime. It turns into a number game. The power of 2 here becomes a coefficient, and the power of x gets reduced by 1. Here, that power on that x is a 1, so it comes down and multiplies the -5. The new power on that x is 0, but x to the power of 0 is 0. That's 6 right there. You could insert x to the power of 0. Excuse me, I misspoke right here. X to the power of 0 on this is a 1, so it's a 1 times -5, not a 0. But on this one, the 0 would moves down and hits the 6, wiping it out. And, well, this is going to turn into a power of -1 times 0. It's just gone at that stage. That's the derivative, and it works for any x whatsoever. If you plug in 1, we should be getting the right slope. Let's check that out. So at 1, y prime is going to be 2 minus 5, so -3. And that's the process. So what we're really studying in section 3.1 is how is the derivative defined in the first place? It's through this kind of work. But we won't be doing this throughout the entire semester. We wouldn't get very far. These would take a long time to get through. We'll eventually be doing our derivatives in this way right here. But any questions at all then, folks, with those last parting thoughts or anything else we did on these notes? Okay, well, I think this is a good stopping point for us. When we go to the weekend, my main objective, really starting on Friday, is to get caught up on grading quizzes. And if you decide to solve this quiz early, I will grade this one early. I usually grade when I have the full set to be as fair as possible and uniform as possible. But this quiz is pivotal. It's helpful for exam 1. If you're working on it early and send it to me early, I'll try to grade it as soon as possible, giving you the feedback before the actual exam itself. But I think that's all we have for today, folks. If you have any questions, I'll be happy to help out. Otherwise, have a great weekend. Oh, and I should mention as well, for folks who turn in their quizzes physically in class, I will scan these and email it to your ISU email address. So you will also get your feedback early. So I forgot to mention that as well.
I have one quick question before I go.
Sure, absolutely.
How exactly did we get that new derivative from the like
Were
the
you
one
referring to
said?
one up here?
Yes.
So there's a interesting formula that goes like this. If you have a power function, it'll be defined in the terms of, or give me one moment. Get that digital tablet requires some special gloves for it to work. So for this function right here, x to the power of n, we refer to this as a power function.
Okay.
And now there's a rule that goes like this. We indicate a lot of the rules in a new notation for derivatives. This d by dx is saying the derivative of something with respect to x, but it's no different than the prime symbol. This is what we're going to introduce in the next section.
Oh, okay.
We put xn right here, and the formula goes like this. This is like putting a prime on xn, or the derivative of xn with respect to x becomes n times x to the power n minus 1. So that's the formula that we're using on all this stuff right here. So derivative of x would turn into a 2x and so on.
That makes sense. Thank you so much.
Yep, you betcha.
And
The proof of that is wild, but that's the formula in the background.
yeah. And as for that confusion with the exam date, it's set for Monday, but my Monday I have another test, and my Tuesday I have classes from 8, no, I think they're from 9:30 until 6:30 p.m.
Oh, hell yeah.
If it's busy like that and I don't think I have like a time slot to fit in the test, could I take it on Wednesday?
Yes, you could. Yeah. For the online section of the class, you folks are required to work with whatever your schedule is and the testing center schedule. So there's an understanding that you might have to adjust a couple days just to get things to fit in, and that would be okay.
Okay, yeah, I don't want to go over too many days because I feel like I'll forget the information and stuff, but it's just the what works with my schedule.
Yeah, that would be totally fine. Absolutely.
Perfect. Thank you so much.
You bet. Have a great weekend.
You too.
The TI 30X8, that one's the good one.
That's this one right here, TI-30XA.
Yeah, that's loud.
Yeah.
Yes. Okay.
If you want one that can do just a little bit more. Oh, dang, I don't think I have anything today, but that's the, this one right here. So
Yeah.
this one it does the same kind of stuff, but you can type in a bunch of stuff in one line. And this calculator, you're reversing order of operations to get things to work out.
Oh.
So whichever one you're best at is
Yeah.
gonna be fine.
I know.
And I think they're like $15 at Walmart or something like that.
Okay. Thank you.
Yep, you betcha.
Where could I take my exam in the disability resource center so I can have time?
Oh, yeah, absolutely, absolutely. Do you know the procedure for scheduling with those folks?
Yes,
Yeah, absolutely. So you can schedule, as I was saying, for other folks, it could
That's all.
be the day of the exam, the fifth.
since I'll probably take it Monday.
Okay, yeah,
I don't think they'll open this like, would the afternoon be okay, Monday afternoon, if I can get it on?
yeah, absolutely.
Okay,
Yeah, for those kinds of exams in that testing center, it's gonna be whichever time of the day works best,
Okay.
absolutely. If you have any conflicts, if they can't get you in on the fifth, they probably should, but if like it filled up or something weird like that, you can schedule for an alternate day that works best.
okay, thank you, have an excellent day.
Thanks, you too.